For our final video on our transformations using sine and cosine, we're going to look at both sine and cosine once again, and this time we're going to look at changing the value of b. Now we haven't done the value of b before. We did a, we did h, we did k, we haven't done b. It's going to be similar to a, except instead of being vertical reflection, stretch, compression, it's going to be a horizontal reflection, stretch, compression. So we're going to open up this graph, so changing the value of b. And again, we're going to look at both sine and cosine. So these are just the parent functions here, just so we can keep going back to those. And we are going to start with cosine of 2x. So notice in this one, your b is 2. Okay? Now, comparing that to the parent function of cosine x, this is a horizontal compression. So with our a, if a is bigger than 1, it's a stretch, vertical stretch. This one is a horizontal compression with the a greater than 1. So think of from this side and this side, taking and pushing in. Now, comparing what's happening here, one full cycle is happening in half the time. So you can think of this 2 right here as meaning 2 cycles happen in comparison to the period of the parent function. So I've got 2 complete cycles between 0 and 360. Let's turn the parent function off again so we can see. So here's my complete cycle. 1, 0, -1, 0, 1. So that's my complete cycle there. Now, my midline does not change. My range does not change. My domain does not change. My amplitude does not change. The thing that changes is the period. So if I'm doing 2 complete cycles in 360 degrees, the new period is 360 divided by 2, which is going to give me 180 degrees. So the thing that changes with b is the period. Now, let's look at cosine of 1/2 x. Cosine of 1/2 x. Whoops, don't have the graph itself on. So there's cosine of 1/2 x. Again, comparing to the parent function. This time I only have half of the cycle in that 360 degrees. Only half of it. So we have 1 full cycle in 360 times 2, or 720 degrees. So this one, when a is less than 1, this one is a horizontal stretch. So it's like you grabbed the graph from this side and pulled out. So we're still getting a stretch or a compression, same as before, except that this time we are doing it from the side instead of from the top or bottom. So it actually kind of flips our rules. Bigger than 1 is going to be a compression, because you're going to squish it from the sides. Less than 1 is going to be a stretch, because you're going to stretch it from the sides. Okay? Now, again, my midline does not change. My range does not change. My domain does not change. What changes is the period. The amplitude does not change. So again, if I'm doing half of a complete cycle in 360 degrees, to do a complete cycle here, I'm going to need 360 times 2, which is the 720. So that's our stretch and our compression. Now, this time we've got cosine of -x. This time we have cosine of -x. Watch what happens there. There's cosine of -x. Now, there's cosine of x. Those are the same. Look at what happens with sine of -x. There's sine of -x. Whoops, I don't want cosine. Here's sine of x. See that that's a reflection? Now, let's go back and take a look at what's happening. What's actually happening here, my 0, 1 stays 0, 1. My 90, 0 becomes -90, 0. I'm multiplying the x value by a negative. I am reflecting it across the y-axis instead of across the x-axis. 180 negative 1 becomes negative 180 negative 1. 270 0 becomes negative 270 0. 360 comma 1 becomes negative 360 comma 1. So with our cosine, what's happening is it's reflecting it across that y-axis, but because it's got symmetry from the y-axis, it's the same, okay? This leads us to a very important little property of our cosine. And here it is, cosine is even. Remember, we talked about that before. So f of negative x is equal to f of x. In other words, cosine of negative x is cosine of x. Those two graphs are the same. Cosine of x and cosine of negative x are the same graph. Now, sine of negative x is actually the same as the graph of y equals negative sine of x. So this leads us to our property for sine. So remember, sine has that rotational symmetry. So, and actually, before we do that, let's compare to our parent function here. There we go. So with our parent function, what's happening, 0, 0 stays 0, 0 because it's on the axis. Then I'm reflecting 90, comma 1 to negative 90, comma 1. I'm reflecting 180, 0 to negative 180, 0. Negative 270, negative 1. Sorry, 270, negative 1 to negative 270, negative 1. And then 360, 0 to negative 360, 0. So I'm reflecting across that x-axis. But it happens that it's the same as if I reflect across the x-axis. So when I graph with a equals negative 1 or with b equals negative 1, for sine, those are the same. So that leads us to our cosine, or sorry, our sine, which is odd. So it has that rotational symmetry about the origin. With our odd functions, f of negative x is negative f of x, which is to say sine of negative x is equal to negative sine of x. Those graphs are the same. That part's not true for cosine. If I do cosine of negative x and negative cosine of x, those give me two different graphs. Cosine of negative x is equal to cosine of x. Sine of negative x is equal to negative sine of x. Okay, and again, that's because of this even odd thing that we've talked about all year. Remember, I told you even and odd functions have special properties. This is that special property we were discussing. Okay, so that is it for our B. Again, we are going to take some formal notes on that, but for now, I just wanted you to kind of have an idea of what was going on when you change that B. It is giving you the horizontal stretch, compression, reflection.